All right, ladies. So we're going to talk about gravity today, right? Okay. You guys know what it is, right? You know that it's a pull between two objects, and it's dependent on what two things? Mass and, well, if you think about the equation for the attraction between two objects, it's dependent on the mass of each object and also how far apart they are. Remember, the equation was, oops, let me get my pen. I forgot. Sorry. The equation was, let's plug this in. Okay. Equation is for two objects. We know it's this equation, right? You do constant, then m1, m2, over r squared. You guys don't have to write this part down. You don't have to write this part down, okay? Now, so we've looked at the math, right? And you probably were introduced to this in grade 11, right? So we're just going to add a little bit more to it, okay? And we're going to kind of go back to some of the things we learned back in chapter 3 with circular motion and gravity. So, what do you think this is? What's this an image of? Yeah, it's an image of gravity. It's a visualization of what gravity is actually doing. Newton is the scientist who kind of like put the math to gravity, right? He's the one who explained what it is, but he didn't really explain how it worked. He said gravity is a pull between two masses, but he didn't really, and then he actually made this really incredible idea that, you know, what's happening on Earth is the same thing that's happening beyond Earth. And if a gravity, like an apple falling to the Earth, that's the same force as the force between the moon and the Earth, and that's why the moon orbits the Earth and doesn't fly off, because gravity's got it in this orbit. And then Einstein came along and he actually put like this picture to it, explained actually what it is. And he explained gravity, and we'll talk more about Einstein later on in this course. But he basically said that gravity is like this curvature of space and time, and that's what you're seeing here. Okay, so any object would bend. That would include us. Okay, but the amount of space and time that we bend is so minuscule that you would never feel it. But a bigger object would bend it, and you would feel it. So what you're actually doing is if you're on a ledge, you're just basically following that curvature, that invisible curve that you can't see. But that's what basically gravity is. It's this curvature. And if you fall, you're just falling basically, oh, I should have picked a different color. You're basically falling down that curve. So you're going down that curve. That's what you would experience or sense of falling. And if the bigger the object, the more space and time are bent. Okay? So this is just the way we visualize it. Now, it was proved, I'm the exact year, that this is actually what's happening because of something called lensing. So I want you to imagine an object over here. Okay? Now, what happens is light from the object is going to travel to Earth. Okay? So here's Earth over here. Now, what happens is when you have an object that basically curves space and time, you have this light that's coming out from the object, but because light is just going to follow that space-time curve, it's going to actually bend. So we can imagine that if we put like a marble here and we let it roll, it'll curve as it goes around that bend. And that's the same thing with light, because light's just going to follow, it's going to travel through space and time, and if space and time are bent, then light will bend. The thing is that we only see in straight lines. So if you have light that's coming out of an object and bending and getting to us, then you would anticipate, and by the way, it's the same thing that happens when you look at something in like a pool. the light bends, you think it's somewhere else because you've seen a straight line, you would actually think that this object is actually in two places. You would perceive it to be over here, and you would perceive it to be in this location over here. And that was actually observed. And that actually proved that gravity is actually just this basically bend in space and time. So that's kind of cool. Thought I would show you that. And then you have something like this, and we'll talk about this a little bit later on. We'll look at the math of this. This is an extreme event where the curve is so dramatic that basically we don't even know where it ends up. This is what a black hole would do. Okay? So we can imagine that the Earth might bend space and time a little bit. Okay? We can imagine that the sun would bend it even more, and then a black hole would bend it to the point where, well, if something goes in, it ain't coming out. Okay? And we'll talk a little bit more about that a little bit later on. Okay? So that's kind of like, who knows where it goes. If you watch the movie Interstellar, they talk a little bit about black holes, and who knows, maybe it goes to some other universe. I have no idea. I've never been in one, so I have no idea. Okay. So, the word, what do you think? So, we have a kind of a picture now of what gravity looks like. What do you think is meant by the term gravitational field then? So what do you think is meant if I say to you, this is the Earth's gravitational field? What do you think is meant by that? Yeah, Chan? Say again? Right. It's the range over which Earth's gravity will exert itself, or where it's acting basically. Okay. So the Earth's gravitational field would be that range where if you're in it, you would feel the effects of gravity from Earth. Okay. If you're outside that field, then you're too far away. And if you look at the equation, there is a point where, R becomes too big, Fu becomes so small that you don't even feel it. Okay? So we're going to talk a little bit about gravitational fields today. But before we get to gravitational fields, let's review, because you guys just got back your gravity labs. Now, we were looking at this before. So when you guys were doing work with things revolving around the sun or revolving around other objects, you may have noticed some patterns, right? So you may have noticed, for instance, that most of the time, not always, I would say probably, I don't know what percent, but most of the time, the path wasn't really circular, right? An object that went around another object usually had what kind of a path? Yeah, it was elliptical, right? What is my... Yeah, so like, for example, in this case, you can see that it's not really a perfect circle. Probably pretty close to a perfect circle. It looks like it's almost a perfect circle. But it's most likely going to be an ellipse. Most likely. So that's when, if you're looking at like the motion of Mercury, Mars, Earth, Jupiter, and you trace it around the sun, it's most likely going to be an ellipse, which means that the distance between Earth, the sun and the Earth is going to change. So whenever you get a number like the distance from the Earth to the sun, that's the average distance. Okay? When are we closest to the sun? When are we closest to the sun? So you think it's summertime? It's actually winter. Yeah. So why is it hotter than in the summer? We're further away. We're actually further away in the summer than we are in the winter from the sun, which makes absolutely no sense. So why is it hotter in the summer then? It's because actually in the summer, where the Earth is, the northern hemisphere is tilted towards the sun, whereas in the winter, the northern hemisphere is tilted away from the sun. So even though we're closer in the sun in the winter, we're tilted away from the sun. So we get less light and it's cooler. Okay, so we're actually looking at Kepler's three laws that explain. So Johannes Kepler was a scientist who studied motion of objects in space, and he noticed certain patterns. And one of the patterns he noticed when he was looking at, I think it was Mars, was that it looked like the objects are traveling often in ellipses around, in this case, the sun. The other thing that he noticed was that, and this is, so his first law was the shape of the orbit, which is things are moving in ellipse. Second thing that he noticed is that the velocity changes. And you probably noticed that when you were looking at your simulations. You'll notice that as the object moves towards the sun, it'll speed up. And as it moves away from the sun, it will slow down. So it will speed up, slow down. Okay, and you can see that here. If you were to, so if you look at Kepler's second law, what he's saying is that if you were to draw a line from here to here, and let's say we were to measure, what's the scale of it? This is we don't know what this is, right? But let's imagine it's just a unit of time. So we said it, okay? So let's say we asked for five whatever units of time of motion. So right now we're here, and let's go actually slow. So we start. Actually, let's do 2.7. So how much area is covered? Well, it would be a line from here to here, all the way to here, right? So it would have covered this area. All of this would be the area that was covered by that moving object. If we were to keep traveling, let's say we did 2.7 seconds from this point to, so if we're at 2.7 seconds, that's about what, 8 seconds? Very close to 8 seconds. So let's say we were to measure the area from here to here to there. So let's imagine we were to measure that area, it would be the same area. Okay? So in other words, if you pick any interval of time, a planet will sweep out the same area. The only way it can do that is that, because if the object is traveling in an ellipse, which is not a perfect circle, the only way it can do that is if the speed changes. It's the only way it can do that. Now, and you can see that. You can see that it's slower here, and then as it gets closer to the sun, it speeds up. Okay? So that's Kepler's second law. And basically, the second law just means that the speed is changing. Okay? That's basically what the second law is talking about. The third one talks about the ratio of the period of a planet and its distance. Now, this actually comes from some work we did a long time ago. Do you remember the equation for centrifugal force? What was it? It was Fc equals mv squared over r. And then we looked at the equation for gravity, which is big G m1 m2 over r squared. And then we were looking at like things orbiting around the planet, right? Like a geosynchronous orbit of a satellite. So we were looking at equating these two together, and we came up with a formula. I don't know if you remember this. It looked like this. And then we realized, well, we can get rid of that. That the speed of a satellite is basically just dependent on gravitational constant times the mass of the Earth over how far it is. And then we took it one step further, where we said, well, V is equal to 2 pi r. So if you square this, you get 4 pi squared r squared equals big G m over r. And then basically, oops, sorry, I missed something, over t. So over t squared. And then basically we have, remember we derived this because we were looking for the distance we would have to put a satellite to get a geosynchronous orbit. So with this, we end up with an equation that looked like this. We had r cubed equals g m planet over 4 pi squared t squared. Sorry. T squared's over there. So there's this relationship between the distance and the period according to this formula. And it's summarized here. So you don't have to go through all of this because the ratio is actually summarized here. So let's look at that with an example for a question, okay? So don't worry about you don't have to write all of this down. We've already looked at this in chapter 3. Okay? So I'm going to erase that. So I just want to show you where that ratio came from. Just didn't come out of nowhere. So let's just get rid of this. So let's take a look at, now how many of you know how far the Earth is from the Sun? You guys, not something you would Google, eh? Like Justin Bieber's birthday, yeah, for sure, but the distance of the Earth from the Sun now. Okay, don't guess. Alright, let's see if we can work it out. So we're going to make, and it doesn't matter what is R2 or R3, just be consistent. So we'll make Mercury number 1. Sorry, no, we're going to make, so see how you have P1 and R1? So we're going to say P1 and R1 refer to Mercury. Okay, and what that means P2 and R2 are going to refer to the Earth, okay? Alright, so in this question here, what are we looking for? We're looking for the average distance of the Earth. So we're going to, that's supposed to be R. So we're going to look for R2. So I'm going to rearrange this and solve for R2. So R2 cubed is going to equal R1 cubed times P2 squared, over P1 squared. Now, P will be the same as big T. Alright? So period, here we're using the letter P. You can use T, same thing. So some books will use P, some books will use T. I got this from a book that used T instead. Okay, so let's plug in some numbers here. So let's figure out that distance of the Earth. So Mercury is 57.9 times 10 to the 6 kilometers away. So it says R1 cubed times the period squared. Now, the period of the Earth squared. I was just about to write the period of Mercury squared. Okay? Over the period of Mercury squared. What's that? No, it doesn't have to be in any unit because it's just a ratio of the numbers, right? You mean your final answer here will be in kilometers just because this unit is in kilometers, but it could be meters. Now, if you're given the distance, make sure that they're in the same units though, right? If you're giving the period, make sure that so if you have one in days and one in years, you got to convert them. They have to be the same unit. All right, so and again, so for our answer, we're going to take the cube root of all of this. Okay, fun times, guys. All right, so what's R2? And by the way, what should it be? Should it be more? Now you know that it's further away from the sun than Mercury, right? At least I hope you know that. Should have done that in grade 9. So we know the answer has to be more than 57.9 million, kilometers. Yeah, 10 to the 6 million kilometers. So what's the answer? (1.5 times 10 to the 8 kilometers. So we got? Okay, look it up now. Google it. See what you get. What's the distance from the Earth to the Sun? And you should be right. What'd you say? 0.6 million? That's to the 8th. It should be 149 million. Did you just say 149 million? Yeah. Oh my god. I thought you said 1.49. Okay, yeah, it's 149. So basically, the number you guys is correct. Okay. So I have some data here that I actually just pulled off the internet that goes over. So here, the radius is in something called an astronomical unit, which basically is the distance that we just calculated for Earth, which is about 150 million kilometers, is one astronomical unit. Okay? So instead of putting all those big numbers in, you could still work with an astronomical unit, which is probably a little bit easier than having to take the cube of whatever, 60 million kilometers. So one represents, again, 150 million kilometers. So Mercury is about 40% of that. Okay. Venus is about 72% of that. Mars is about 1.5 times that distance. Pluto is almost 40 times that distance. Okay. So these are the numbers for the planets. Pluto's, I don't know if you know, Pluto's been demoted. Yeah. Yeah. My daughter was doing that for a science project. Anyways, and this is the period. Again, so instead of having it in days, what they've done is they said, or years, basically, Earth year is considered 1, and all of these then would be in relation to that. So like, for example, Mercury's orbit has a period of about 24% out of the Earth. So about 4 times less. So 88 days is just 365 days, okay? Pluto, 248 times longer. Okay. So how old would you be on Pluto? You'd be the same age, but well, actually, yeah, you should be the same age. Well, we'll talk about the effects of gravity on aging later on in this course. But I would imagine you should be the same. But you would be, if you had birthdays, you wouldn't be celebrating your birthday. You'd be dead for your birthday. Because look, well, first of all, you couldn't survive on Pluto because Pluto is very, very cold. It doesn't have the raw materials for survival. But if you could survive on Pluto, 200, you'd have to wait 248 years for your first birthday. So what I've done is I wanted to see the math, like just if you were to graph this out, and then just to show you how close Kepler was and how accurate his predictions were. These are just numbers. So for example, if I put the number 1, 2, 3, 4, 5, 6, 7, 8. So this column would be the square of that number. Because remember the relationship is r squared. Was it r squared or r cubed? It's r cubed. It's p squared, right? I have these backwards then. It was r squared and p, no, r cubed and p squared. I have these backwards, sorry. So this is the, okay, so that's t, and that's r. I apologize, ladies. Okay, so one of them, so this one is cubed. R will be cubed, here will be squared. So if I put up a number like 1 to 8, this is the number squared, and this is the number cubed, okay? So if you graph these two, you get this. Okay, there's the function for that. And then we can ask for a trend line. And it's a polynomial. Okay, and there's the equation. Alright, now we can do the exact same thing for the other one. Set them beside each other. Okay. And I can graph these two, and you'll see, like this model is very accurate. We put them beside each other. Oops. Oh, what happened? Disappeared. Okay. So it looks like he got it right. Very close. Look at the equations. Okay. Very impressive. That he can make observations about our galaxy and be like pretty much bang on. So here, that's pretty cool. Okay. Anyways, all right. So we've talked about visualizing gravity. We've talked about the relationship between the period and the orbit of the distance of a planet from the sun. So let's talk about energy now. You guys remember the relationship between energy and force? We studied that in chapter 4, right? And that was just a review from grade 11. You recall this stuff? Yes? No? You guys also, you probably learned in grade 11 that the energy is the area under a force distance graph. You guys remember that? Because work is defined as force times distance. Okay, so which of these three graphs would represent, I left the arrow, should have erased it. Obviously you're going to know the answer then. Which of these three represents the energy for the graph that would represent or visualize gravity? Which one? So we talk about gravitational potential energy. And we know the relationship between energy and force is, energy is just the area under the force distance graph. So which of these three graphs would represent the energy, the gravitational potential energy? Has to be which one? Kind of left a hint here, guys. But I forgot. Take out the, oh, he's winking now. Why is it this one? What kind of a relationship is this equation? How many of you guys have heard the inverse square law? Basically, it's 1 over x squared, and if you were to graph that, it looks like this, right? So this would represent the area underneath that curve. Now, it's easy to figure out the area for a curve like this, or like this. It's much harder. You need to do some calculus. Now, the last time I did calculus was 1991. So if we go to the internet and we ask for events in 1991 events, oh, the internet's not working. Hold on a second. Let me use my own internet here because our Wi-Fi is not working. What is it? Okay. Just out of curiosity. Let's try this now. Let's refresh. 1991. On this day, 1991. Or what happened in 1991? Okay. Oh, Kuwait? What happened? We had Desert Storm. Dead Sea Scroll was unveiled in 1991? Wow, look at that. Canada introduces the goods and service. The GST was introduced in 1991. Wow, I didn't know that. Was it 91? Okay, anyways, my point is a long time ago. Jeffrey Dahmer is arrested. Wow, you know who Jeffrey Dahmer is? He's the guy who he killed people and then he kept them in his basement and he ate them.
What?
Yeah. Yeah. Russia was still the Soviet Union. Wow. Okay. Anyways, you get the point. It's a long time ago, so I'm not going to go into calculus because I don't remember it. So apparently, you could figure out the area under that curve by using, I guess it would be the antiderivative of that curve. And I'm not going to go into that. So I'm just going to give you the equation, which has been derived for you. So here is the equation for the area under that curve. Okay. So any 2 points. Now, we've defined work as what? Change in energy. So that would mean what? EF minus EI. So you're looking at this. This equation looks funny, doesn't it? Because you got a negative sign in it. You have negative here minus another negative. That looks a little odd. I'll tell you why they did that. R2 would refer to a distance further away, and R1 would be something closer. Now, you know that if we did that, if you take an object, let's say it's a block, and it's resting on the ground, okay? Let's say we took a block, and let's say the block had a mass of 1 kilogram, and you lifted it at a height of 10 meters. How would you figure out how much gravitational potential energy you added to it? What was the equation you learned in grade 11? Yeah. It's mgh, right? It was the potential energy is the mass times g times delta h. So h2 minus h1. In this case, because h2 is at the ground, h2 was considered to be what? 0, right? This equation that we use in grade 11 works really well for something at the surface of the Earth. But here's the thing. When you really think about the gravitational attraction between the Earth and an object, where is it really pointing? Is it at the surface of the Earth? No, it's all the way at the center of the Earth, right? So now here, if we did this calculation, you would get a positive answer, right? Because you would have 10 minus 0. If you did the same thing with this equation, you would get a negative answer, which doesn't make any sense. Because if R2 is further away from the Earth, that means this number is what? Smaller. And if you use delta, like final minus initial, then you would have a smaller number minus a bigger number. What would you end up with? You end up with a negative number, right? So that's why those negatives are in there, because your energy should be positive, not negative. Okay? So how much energy? So let's take a look at this equation. Okay? How much energy is required to change the height of a rocket? Make this a little bit smaller so we can see it. Okay? See that? mass is 1,000 kilograms from the surface of the Earth to a height of 200 kilometers above the surface of the Earth. So first thing we got to remember is that now we can use the old equation to see how close our answers are. When the difference between R2 and R1 are very small, chances are both equations will work. But as they become more different from each other, then you're going to have to use this new equation. Okay? So let's take a look. What's the diameter of the Earth, first off? What was the diameter? It was 6.4, I think it's 6,400 kilometers, right? Now this has to be, Alex, going back to your question, this has to be in meters, okay? So this has to be 6.4 times 10 to the 6 meters. All right, so we're going to take an object at the surface of the Earth, which is actually 6.4 million meters away from the center of the Earth, and we're going to lift it height of 2,000 kilometers. In other words, now maybe I should just use R instead of D, okay? So I'm going to change this to R. So this is R1. Now we're going to talk about R2. Well, what would R2 be then? It would be not 6,400 kilometers, it would be 8,400 kilometers, right? So it would be this, which means it's going to be 8.4 times 10 to the 6 meters. Okay? So let's take a look at our equation. So we have work is equal to negative G. Now, remember what G is, right? G is that really big number of that really small number, not big number, it's tiny number. Okay? Times the mass of the planet, which was what? What's the mass of Earth? About 6 times 10 to the 24 times the mass of the rocket. Okay? Over. Now, I don't know how to draw a line anymore, so I'm going to get this. Alright, there you go. There's my line. Okay. Over R2. R2 was 8.4 times 10 to the 6. And we're going to subtract a minus. So we're going to add same thing. Okay. Can I erase these numbers now? Because I'm going to run out of room here. Yeah. I think it's. I mean, why isn't it just negative G M M over R2 plus? I'll show you why next. Yeah, it actually has to do with the next topic. Because if R let me think about that one. We'll come back to it now. Okay, so it's going to be plus, so 6.6. Change the thickness of this pen. Times 10 to the negative 11 times 6 times 10 to the 24 times 1,000 okay. We're almost done, guys. This is a lot of work here. Okay. Over 6.4 times 10 to the 6. Okay. All right. What's the first one? What's this? Negative what? What is, sorry? times 10 to the 22. Okay. And are you sure?
Yeah, I thought negative 4.5 times to the negative 10 to the 10.
Yeah, that makes more sense. Times 10 to the 10, right? Okay. Plus, what's the second number? So 6.25 times 10 to the 10, and now we add them. So that would be, should be 1.45 times 10 to the 10. Okay. Now, okay, what if we use this equation? The work is just mg delta h. So 1,000 times 9.8 times 22,000 kilometers, which would be 2 times 10 to the 6. So this is the equation you would have used in grade 11, right? Work is equal to the change in energy, in this case the change in potential energy. What would the answer be here? What is it, Nika? 1.96 times 10 to the 10. You'll notice that they're not the same. Okay? And that's because the first equation works all the time. The second one, the one you learned in grade 11, works over short distances at the surface of the Earth. Okay? But the problem is, as you go away from the surface of the Earth, the further you go away from the surface of the Earth, something's going to change in the second equation. What would it be? Little g. Yeah, little g. Little g is not going to be 9.8, 2,000 kilometers away from the surface of the Earth. So, which answer is right? This one. This one's going to be the right one. Okay? Now, what happens when we approach infinity? Well, then what happens to, if R2 approaches infinity, what does this become? It becomes 0, right? Okay. So let's talk about this then. What if I ask you a question? How much energy would it take on the Earth, okay, and you say you're a rocket ship, not you're a rocket ship, but maybe you have a rocket ship, it's blasting off, and you want to know what is the minimum amount of energy that you need. This obviously would be kinetic energy to escape Earth's gravitational field. And what we mean by that is we're going to get to a point where we know that there's a certain amount of force, and it's the strongest at the surface. Well, it actually would be the strongest at the center, but we're not the center. We know that as we move away from the surface of the Earth, the force is going to get weaker and weaker and weaker and weaker until we get to a point where there is no more force between the rocket and the Earth. Okay? And so what happens at that point? Okay? Now, if you have the minimum amount of energy, that means that as you're taking off, okay, the Earth is going to pull you back. It's going to try to pull you back. What's going to happen is you're going to have a certain amount of speed. You're going to start slowing down. Because it's still, as long as you're in this gravitational field, which way will the rocket accelerate? After it's not accelerating anymore, right? And it's traveling through Earth, through space. And there's only one force acting on the rocket, which is the gravitational field or gravity from Earth. What will happen to the rocket? Will it accelerate or decelerate? It will decelerate. If we can get to the point where we escape the Earth's gravitational field, so in other words, Fg equals 0, but the rocket ship has no more kinetic energy, then we get to a point where we basically figured out what the minimum velocity is to escape that planet. Okay, this is called the escape velocity. Right? So we can think of it this way. This is the amount of energy that the rocket ship has in terms of gravitational potential energy. Out here, it has no energy at all. Okay? Out here, Eg is 0, Ek is 0. So it would make sense, so we're talking about the escape velocity here. So at that point, when we escape that gravitational field, there's no more energy. So we can think of this. Here's the total energy of my rocket ship. So at the surface of the Earth, when the rocket ship isn't moving, which of these two does it have? Ek or Eg? At the surface of the Earth. Yeah, it has this. But when we escape the gravitational field, it should only have this. And this, sorry, other way around. I wrote it backwards. At the surface of the Earth, it only has this. When it escapes the gravitational field, it needs to have, in order to escape the field, it needs to have a certain amount of kinetic energy. That has to be equivalent to that initial potential energy. So, let's figure out how fast you would need or what would this minimum speed a rocket would need to take off from the moon to be able to escape its gravitational field. Now, the moon is not the Earth. Okay, so can someone Google the mass of the moon? And the radius of the moon? So what's the mass of the moon? Yeah. Okay, and what's the radius of the moon? $1,700, which will be 1.74 times 10 to the 6 meters. Okay, so our potential energy is this equation. So this equation is negative gm m over r1. Because R2 number is the point where we've reached where there's no more gravitational field, right? So R2 basically makes that part 0. So right now we're on the moon. So what would be that potential energy on the moon? What would it be? So it's negative 6.67 times 10 to the negative 11 times the mass of the moon times the radius of the moon sorry, no, that's not what we play. Not the radius of the moon, mass of the moon, mass of the rocket. Okay. Times the mass of the rocket. The rocket is 1,000 kilograms. Okay. Okay, over R, which is, okay, so it's G, so here's G, mass of the moon, here's the mass of the moon, mass of the rocket, here's the mass of the rocket, over R, because the rocket is on the surface of the moon, so we're just going to be concerned with the radius of the moon, it's 1.74 times 10 to the 6. So what's the energy of the rocket at that point? How much energy does it have? What is it? 2.8 times 10 to the 9? Okay. Now, the equation is how much kinetic energy do you need to escape the gravitational potential? Would be this. Ek equals negative the potential energy. So, our kinetic energy is going to equal positive 2.8 times 10 to the 9 joules. The kinetic energy of a rocket is what? It's half mv squared. So it's going to be 1/2 mv squared is going to equal 2.8 times 10 to the 9. We could get rid of the half, and we can get rid of the m, and then we can take the square root of this. Okay. So, now we did a little bit of extra work, and I'm going to show you another equation. I know, so but tomorrow I'm going to give you guys a work through it. So instead of doing 2 parts today, we'll do it all today. All the theory in chapter 6, and we're done tomorrow. Okay? What is it? We'll say 74 meters per second. Now, we did some extra steps. This is the first time we're looking at it. But basically, if you think about what we're doing here, right? We have 1/2 mv squared is going to equal basically G, m moon or m planets, and then m of the object over R, right? You'll notice that cancels out. So you're left with, and we can get rid of the half. So you're left with this equation. Now, what this equation is the escape velocity equation. Okay? So as long as you know how big the object is that you want to escape from, the radius to the center of that object, you should be able to figure out how much speed you would need to escape that object. So we can figure out the escape velocity from Earth. Okay? How fast would a rocket need to be in order to escape the gravitational field of the Earth? But what's really cool about this, we can take it one step further, and we can figure out a question like the last one. Now, the Schwarzschild radius has to do with a calculation that was done, I believe it was 1916, when Einstein's theory of general relativity explained how gravity worked. One of the things that came out of that was this idea of black holes, which he talked about, which is basically when space-time is curved really so much that light can't escape. So we can ask a really neat question. How big would the Earth need to be to become a black hole? To the point where if we are on Earth and we were to shine a beam of light from the surface of the Earth, and you were off the Earth, let's say you were on the moon, and you were waiting for this beam of light from the Earth, you would never see it. In fact, you wouldn't even see the Earth, because no light would escape from the Earth. Okay? How big would the Earth need to be, though, for that to happen? Well, we can take this equation, we could rearrange it, and we could say this. We could say, we looked at that part, we could say R equals G, M planet, over V squared times 2. So how big would the Earth need to be? Well, big G is 6.67. The Earth is 6 times 10 to the 24. This is times 2 over V squared. Now what's V? What's the fastest anything can be? Speed of light, which is what? 3 times 10 to the 8. 3 times 10 to the 8 squared. Okay. So, how big does the Earth need to be? Or how small would the Earth need to be for it to be a black hole? So, by the way, if you come across this equation in textbook, it probably won't use the letter V. It'll probably use the letter C. So they'll probably use C squared, because C represents what? The speed of light. Okay. So what's the radius of the Earth? Nah, sure. That's not the radius of the Earth. Sorry. Say it again. 0.009? Okay, so yeah, so 0.0. Now this is in what? Meters? Right? Wow. I can't visualize that. Can you visualize that? What is that? That's 9 millimeters? I'm assuming we did the calculation correct. I'm assuming we did it right. Everything's good. So, wow, I can't imagine having the entire Earth into an object that's less than a centimeter in radius. Wow. That's kind of weird. That's bizarre too. Alright, so we've talked about gravity, we've talked about ellipses and the the behavior of orbiting objects. We talked about gravitational potential energy, we talked about escape velocity. You can even calculate how big we need to be a black hole. Well, you're not a round object, so it'll be hard for you guys. So that's it. That's it for chapter 6, basically. Okay. So we are done.